All right, in the last few sections, we've been talking about probability theory quite heavily. We talked about probability in the context of isolated systems, and then in the last section we talked about probability for open systems, the Boltzmann distribution. But we've never formalized the idea of probability. We've never talked about the general properties of probability, and that's a weakness that we should remedy now. So this is from chapter 12 of Engel and Reed. And they do a pretty good job of talking about single variable probabilities and probability distributions. There's also multivariate probability. That's a bigger topic. And I won't talk about that really at all either, except as needed as we go along. So this whole section is about single variable or univariate probability. First of all, in order to talk about probability, you're asking what's the probability of a certain outcome or a certain event or a certain microstate in the cases that we're most interested in. But in all cases, there's some set of possible outcomes. And the very first job when talking about probability is to figure out or think hard about what that set of possible outcomes is. You're doing some experiment, some set of possibilities exist, other things are not possible. You exclude all the things that are not possible, keep only the things that are possible, and that's your set of possible outcomes. In general, for our class, the set of possible outcomes will equal the set of microstates for the system of interest. So in our case, it's pretty easy. It's pretty cut and dried. You define what microstates are possible for the system. That's also your set of outcomes for the most part. Here are some examples of outcome sets. Let's suppose that your system is just one two-state system. So a spin that can be either up and down, for example, and just one of them, not a bunch of them, just one. Then there's only two quantum states, there's only two microstates, and that means there's only two possible outcomes in your set of outcomes, and that's the whole thing. 0 and 1 is your entire set of outcomes. Let's suppose now that I have a slightly more complicated case. I have 3 of these two-state guys. So 3 spins or whatever. Now, a set of outcomes could be, I have to specify the state of each one of my 3 independent systems. So a single outcome would be ground state for system number 1, ground state for system number 2, and ground state for system number 3. I can call that 0, 0, 0. That's one outcome. But I could also possibly have been in the upper state for system number 1 and in the ground state for the other 2. That would be outcome 1, 0, 0. Or I could have outcome 1, 1, 0, or 1, 1, 1, or 0, 1, 1, or any of these possibilities. Those are all possible outcomes, but now obviously there's more than 2 of them. In fact, since there's 2 choices for each of 3 molecules, there's 2 to the 3rd power, or 8 possible outcomes, and now that's your outcome set. If you have, in general, a large number of molecules, then it's clear that, and they're all independent, then the size of your outcome set is going to be W, which is equal to the number of possible outcomes per molecule to the number of molecules power. And we will encounter that kind of behavior quite a bit in what comes next. All right. Another possibility is that I have a single gas phase molecule, let's say a water molecule. Well, that water molecule has a bunch of internal degrees of freedom, right? It's got rotations. It's got translations. It's moving through space. It's got internal vibrations. And so I have to specify something. I have to say something about each of those possible degrees of freedom. For the translations, there's momentum, and I gotta specify that momentum. For rotations, there's angular momentum quantum numbers. For vibrations, there's vibrational quantum numbers, and then there's also electronic quantum numbers that give the electronic state of the molecule, and all of those are necessary to specify the quantum state, the microstate, for just one molecule. And now if you have many molecules, of course, you've got to do that for each and every molecule, and that means you're going to have a boatload, something like this, of possible outcomes in your set of microstates or your outcome set. All right. We've been talking so far only about discrete cases where each of the possible outcomes can be labeled with a discrete index, something like an I or an N or a J or a K, an integer. But there's a lot of possibilities where the set of states you're interested in is a continuum. So the set of all positions that a molecule can occupy, that's a continuum. The set of momenta that momentum a molecule can have, that's also oftentimes a continuum. And there are many other continuum variables or continuum physical parameters that we'll encounter when we're talking about the various cases that we've talked about. This complicates probability a little bit. We'll talk about continuous probability distributions a little bit further down. But first we'll talk a little bit more about the discrete cases. They're easier. What we're going to do next is assign a probability to every possible outcome in your outcome set. In other words, we're going to assign a probability to every microstate in our physical system. Each probability tells us something about the likelihood, or tells us the likelihood that we'll encounter that particular outcome or that particular microstate. All such probabilities have to be greater than 0. There are no negative probabilities. And they have to be less than 1 as well. So all probabilities are bracketed or limited to the range between 0 and 1. If it isn't bracketed or limited in that range, then it's not a probability. It might be something closely related to a probability or something else like that, but it isn't a probability proper. All the probabilities have to add up to 1. And now you can see why the individual probabilities have to be limited between 0 and 1. You can't sum up a bunch of positive quantities and get something and have them all equal 1 if one of them is greater than 1, certainly if more than one of them is greater than 1. The reason we require this, we require that they all add up to 1, is that when we're adding them all up like that, what we're really doing is calculating the probability that I land somewhere in the outcome set. And the probability of landing just somewhere in the outcome set, anywhere at all, that's got to be 1, right? I'm certain to land somewhere in the outcome set. And so the probability for that has to be 1. All right, here's what probability distributions look like. Here's a sort of generic case. My outcome set only has 5 elements in this case. 1, 2, 3, 4, 5. There's a probability associated with each one of them. All those probabilities are positive and less than 1. And if I actually assigned numbers to these and I added up all these columns, I would get a total of 1. Here's a case that we've seen before, the binomial distribution. We saw this early on in the class. Here's the actual mathematical expression for each of these probabilities in all these bars. It's a nice peaked distribution, and we've seen some of its properties earlier. I won't talk about them now. This is the binomial distribution for the case where n is equal to 6, in which case there are 7 possible outcomes, 0 through 6. And again, if I add up all these bars, I'll get a 1. All right, suppose instead of wanting to know the probability for just one value, like 2 here, that instead I want to know the probability for a 1 or a 2 or a 5. In other words, for some subset of all the possibilities in the outcome set. Then the probability for that subset is just the sum over all the elements in that subset. So if I want to know the probability for a 1 and a 2 or a 5, any of those will do. Then I just add up the probabilities for 1 and 2 and 5, and that looks something like the area under the curve associated with those possibilities in our outcome set. Okay, it often happens that what you actually get to start out with isn't probabilities. You get some set of numbers R, and they're all positive. None of them are negative. You can't have negative values, even in this case. But they don't all add up to 1. I add up all the r sub i's and I get something greater than 1 or less than 1. It's got to be exactly 1 if they're probabilities. And so if they don't add up to 1, then they're not really proper probabilities. But that's fixable, because all I need to do is rescale all of these. I need to basically multiply or divide all those r sub i's by a fudge factor, and then I can make them add up to 1. And so what we say is that the probabilities we actually want are these numbers that we have divided by some fudge factor, which we call the normalization factor, and we adjust the value of that n in order to make everything add up to 1 properly. So I say, I want all the probabilities to add up to 1. Each of the probabilities is an r sub I divided by this fudge factor. The fudge factor factors out because it's not part of the sum, doesn't depend on I. And that result has to equal 1 over here. And therefore, n has to just be the sum of all the r sub i's. And now you can see that that's going to work. The probability is now r sub I divided by the sum of all the r sub i's. That means that if I sum up all those guys, I'm going to be summing all those guys, right? All these r sub i's divided by n. That means I'm summing all the numerators divided by n, which is also this same sum, and that's going to give me 1. So that's going to work. That's called normalization. All right, now we've seen enough. Let's do an example, and of course the example we're going to consider is the Boltzmann distribution. That's the case that we're by far and away most interested in. For the Boltzmann distribution, as we've seen, each of the probabilities involves one of these exponential guys that we call a Boltzmann factor. But if I add up all of those guys, I don't get 1, right? So these are not the probabilities per se themselves, but we're going to do our normalization trick and fix that. So according to the rules we got up here, right, this normalization factor should just be the sum of all my original things. These are my r sub i's, right? In this case, these exponentials are my r sub i's in this case. So if I just add up all those r sub i's, I should get a proper normalization factor. And we recognize that sum. That's our q that we already got from the Boltzmann distribution up above. And that means that our proper probabilities are just the Boltzmann factors, the exponentials, divided by the normalization factor, which we call q in the context of statistical mechanics. And we've seen that this is normalized. They all add up to 1. And so now we know where that q came from also up in the Boltzmann distribution. Another example that doesn't really apply directly to statistical mechanics, but does show up often enough to be of great interest, is the idea of normalizing a histogram. So let's suppose I take a bunch of measurements of some kind. I'm measuring some quantity x. I measure it a whole bunch of times. In fact, let's just say I measure it 64 times. So I make 64 x measurements, and then I bin those measurements. If the x value fell into this little bin, then I count up how many times something fell into that bin, and if it was 12 times, then I put a 12 there. I do the same thing for all the other bins. So 20 in that case, 7, 15, and so on. Those bars just represent the number of times each x value fell into particular bins in my histogram. But obviously these bars, these are the raw numbers or the raw data. And they don't add up to 1, right? I add up all those bars, and in fact they add up, these are the h sub i's. So histogram bar number I here. If I add up all those h sub i's, that is the number of measurements that I took, right? Which in this case is 64, but it's also the normalization factor in this case. So now I divide all these bars by 64, and I get proper probabilities. So about 20% in this case, about 30% for that one, 11% for that one, 23%, and so on. And now if I add up all those guys, I am going to get 1. And in fact, here they all are, all added up, and indeed you do get 1. So this is a normalized histogram, and therefore represents a proper measured probability distribution, right? This is how you actually experimentally measure a probability distribution. Okay. I mentioned up above that in some cases your outcome set is on a continuum, so positions, for example, x. And in that case, the probability business that we talked about up above is a little bit more complicated, not much more complicated, but a tiny bit more. The difficulty is that if I ask, what's the probability of being at some absolutely single point on the continuum, that probability has to be 0, right? Because there's no finite chance of hitting one exact point on a continuum. A continuum is a bunch of packed points. You can't hit one exactly. You can only get close. And so instead of asking about a single point, we ask about finite little intervals or tiny little intervals. We ask, what's the probability of being somewhere in that interval, not at a particular point? And to put that into useful form, we define a function called the probability density and multiply it by the length of that interval. And we say that the probability of being in the interval is equal to the probability density times the size of the interval. That means that this probability density, so I didn't say this, but let me say it up above, all these probabilities up above, these all have to be unitless. Right? Probabilities don't have units, but probability densities do have units. So down here, this probability density, this whole thing has to be unitless. The whole thing does. Let me erase that arrow. So all of this has to be unitless. But this, for example, if that's distance, might have units of meters. That means in order to make the whole thing unitless, the probability density must have units of 1/meters, and therefore probability densities do have units. And sometimes that matters, and you got to be careful about that. And that's what I'm saying here, in fact. So in that case, you've got a probability density, which looks a lot like the discrete probability distributions we looked at in the last section, except it's continuous. It's a function. And if I want to know the probability of finding myself in some little interval like that, then I just multiply by dx, and that's my probability. The smaller the dx is, the smaller the probability. The wider the dx is, the wider the probability. And that suggests that if I want to know the probability not of being in a little tiny interval, but being in some broad interval between x0 and x1 here, anywhere in that whole zone, then all I have to do is integrate, right? This is just like summing over the probabilities that we talked about last time, right? I said, what if you want to know the probability of being of some subset of your outcome space? Well, you just add up the probabilities. That's all we're doing here. Here's our subset of our outcome space, and we're just adding up all the probabilities in that outcome space. That means integrate under the curve, and this is the area under the curve, right? The area under the curve in this case is the probability of being somewhere in that interval. All right. Probability densities, like probabilities proper, have to be between 0 and 1 for the same reasons too, and they have to integrate to 1. If I integrate over this whole curve from here to here, I have to get 1. So the area under this whole curve has to be 1. And that means that the same kinds of issues that come up with the discrete case also come up with the continuous case. I often will find some function that isn't a probability density because it doesn't add up to 1. It doesn't integrate to 1. The integral of f of x dx is not equal to 1. And so it's not a probability density, but I can normalize it basically by putting in a normalization factor, a fudge factor. The normalization factor is the continuous analog of our normalization factor for the discrete case, right? For the discrete case, it was this. It was the sum of all the r sub i's. That was the normalization factor. Well, now we've got a continuum, so instead of a sum, we've got an integral, but otherwise it's the same thing. And so my normalization factor here is just the integral of my trial f of x over all the possible outcomes. And so this guy, the f of x divided by the normalization factor, is a proper probability density. This should also all be familiar from quantum mechanics. You had to normalize wave functions before, remember, from quantum mechanics. And normalization is an issue that comes up right away when you do any kind of quantum mechanics as well. So if you can remember back all the way to the last semester, then this should all be familiar, I hope. All right, let's do an example. Let's consider a continuous Boltzmann distribution so far. We've up to now considered discrete Boltzmann distributions, right? So discrete energies, a discrete set of energies. I is some integer index. But suppose I have a quantum energy or a classical energy, it doesn't matter, that depends on a continuous variable instead of a discrete index. In that case, I have a continuum of possible outcomes, and let's see how that looks for this particular case. So I'm going to consider a diatomic molecule. Normally, it wants to be at its equilibrium bond length, but I can stretch it a little bit, or I can compress it a little bit. And when I do that, its energy rises, right? When it's at its equilibrium bond length, it's at its minimum energy. But when I stretch it or compress it, I'm raising its energy, and the energy I'm raising it by is a good approximation for that anyway, is a harmonic oscillator. So 1/2 times the force constant, kappa, times x, where x is the difference from my equilibrium bond length. So I consider r out here. If it's greater than r0, then x is a positive quantity. If r is less than r0, so if they're close together, then x is a negative quantity, but I'm going to square it, so it doesn't matter. Same energy both ways. All right. A Boltzmann factor, a Boltzmann distribution, is always e to the minus energy over kt, or e to the minus beta energy of some kind. In this case, here's our energy, so we're going to put that up in place where energy goes, and that's what we've done here. I've put my bond stretching or compression energy up there in the energy place, in the energy slot. And that means that I want my probability distribution, my Boltzmann distribution, to be this function, but I got to normalize it. This by itself is not yet normalized, and I got to fix that. Normalizing means doing the integral to get n, and in that case, that means doing this integral down here. So I'm integrating. Well, I kind of did this in a funny way, so let me do it a little bit more properly. I'm integrating the integral from minus infinity to infinity, right? My outcome set can be anything because x can be anything. In principle, I can stretch the molecule as far as I like, or I can compress it as far as I like. And so it can be from minus infinity to infinity of e to the minus, what was it, kappa over 2kt x squared dx. That's what should go in there. And what I've done is just change all this stuff to a. I've made a simplification to make things easier. This integral is, you can look up in tables, it's a dead standard integral, and here's the answer. And if I plug in the value for a there, a is equal to, here it is, a is equal to kappa over 2kt, then I get that my normalization factor here is just this square root quantity. And so if I put that underneath, then my proper normalized probability distribution is just a normal distribution, or a Gaussian distribution, it's sometimes called, which is a bell curve, a peaked curve, and we could talk on the normal distribution, like the binomial distribution, and is just the most common distribution there is in all of statistics. And so there's lots to say about it, but we'll leave that for another day, or for another class even, maybe. So if I change the temperature, I'm making all of this quantity smaller, and what that does is if I make the temperature smaller, well, if I decrease the temperature, I'm making all this bigger, actually. And if I make that bigger, then I'm making the distribution narrower and taller. If I increase the temperature from that, then I'm making it wider and shorter, and increase it still more, and it gets even wider and shorter. And that makes physical sense, because what that's saying is that when I'm at low temperature, the molecule can't vibrate very much, doesn't have enough energy to vibrate very much. When I'm at a higher temperature, there's more thermal energy around, it can vibrate over a wider range, and if I raise the temperature still more, it can vibrate over a still wider range. So all of this makes perfect sense, and there's lots more to say about this, but we'll bring that up again later when we talk about harmonic oscillators and vibrators and that kind of thing. All right, so that's some of the basics for both discrete and continuous distributions. Now let's talk about the last major subject for this whole topic, and that's expectation value. The expectation value is basically a weighted average. And it's defined in the following way. Let's suppose I have some quantity z that's associated with every possible outcome or every possible microstate. So for every microstate in my set of possible microstates, I've got some z. It might be energy, it might be position, it might be momentum, it might be angular momentum, it might be anything else. Doesn't matter what it is. Whatever it is, I put that into this sum and I multiply it by the probability for that same microstate. So I take the property I want, I multiply it by the probability for that microstate, and then I sum over all the possible microstates, and that gives me my weighted average, right? These are the weights. The probabilities are the weights. And here's my quantity of interest, and I'm weighting each of those quantities by the probability, summing over them all, and that gives me my weighted average, which is my mean value for z. And there's a continuous version of that too. The only difference is that instead of just a set of discrete z values, I have a function, right? A continuum of possible z values. Any function z of x at all can go in there. Doesn't matter what. I can put whatever I like in there. We'll see an example of it down below. I multiply it by the weight, which in this case is the probability density. And then I integrate the whole thing over all the possible range of my continuous variable. And that gives me the weighted average, or the expectation value for z in the continuous case. There are two special cases. So this is the general case up here, but there are two special cases that come up all the time and are especially important. And those are the mean of the distribution and the variance of the distribution. The mean, everybody kind of knows what the mean is already. It's some measure of the center of the distribution, or a representative value of the distribution. And the variance is some measure of the width of the distribution. So this is sigma squared is the variance, and sigma is the standard deviation. So that's why these guys are important. They're called moments of the distribution in Engel and Reed. And they characterize to some extent what the distribution looks like. And sometimes you can get means and variances even when you don't know what the distribution itself looks like. And that tells you something about what the distribution looks like, even if you don't know it in detail. All right, so the mean just means take my x value, whatever it is I'm measuring, multiply it by my probability density, and integrate over all the possible outcomes in my outcome set. That gives me the mean. The variance is more complicated. It means take the value that I'm interested in and subtract the mean value. So these guys in here are delta x's. They're differences from the mean. They're quantities like this down here. So here's the mean. Here's the some value of x, and the difference from the mean, that's the delta x. And then I square that, right? And I square it because I want to add up these differences, but I don't want them to cancel. I don't want a difference over on this side to cancel this difference. And the way I prevent that is by squaring this guy, which makes them positive on both sides, no matter which way the difference is. And then I add those guys all up, weighting them, each one of them, by the appropriate probability, or in the continuous case, weighting it by the probability density. And I either do this sum or I do this integral, and that gives me the variance. Then the standard deviation is just the square root of the variance. So here's the variance, here's the square root of the variance, and sometimes that square root of the variance is also called the root mean square value, because you're taking a root, you're taking a mean, and then you're taking a square of the quantity of interest, and so it's a root mean square quantity. All right, as I said before, the variance is a measure of how wide the distribution is. Small variance means you've got a narrow distribution. Big variance means you've got a wide distribution. It is possible to take expectation values or weighted means like this for any quantity whatsoever. The mean and the variance are not the only possibilities. So, for example, I said before that if you've got some function z of x, you can calculate an average value for z. So in this case, I set z equal to this exponential function. I can put any function in there at all. I could put a cosine in there. I could put a log in there, anything at all. I put that into my integral. I multiply by my probability density. I do the whole integral, and that gives me my mean for this particular quantity. It's the expectation value or weighted average value for these exponential quantities, whatever significance they may have in a physical setting. All right. There is one more topic that I want to talk about before we end this section, and that's the fact that in statistical mechanics especially, there are a lot of what are called multivariate distributions. So what those are is where our probability density or probability proper, discrete probability proper, has more than one variable. So there's not just an x, there's also a y, and there might be an x and a y and a z, and there might be an x1, x2, x3, all the way out to 100. You can easily have probability distributions that depend on many, many variables. In fact, in StatMech, you can have probability distributions that have Avogadro's number of variables, 10 to the 23rd variables. That's a multivariate probability distribution. So these things are encountered in great numbers and great variety and great complexity, especially in StatMech, but there's also a lot of rules that govern multivariate distributions, and this is not a class in statistics, and so we're not going to spend time going over the general rules. What we'll do instead is go over each of the rules as we encounter them going through the rest of the StatMech. However, we have already encountered one of these cases, and that's up when I was deriving the Boltzmann distribution. I said that if I have a system and it's surrounded by a big surroundings, and if the system and the surroundings are statistically independent, then the number of states in the whole thing, cis and cir together, is equal to the number of states for cis times the number of states for cir. This requires statistical independence. And if this is true, then the probabilities will also be statistically independent. So the probability of finding a state in cis, the probability of finding a state in both cis and cir is the probability of finding a state in cis times the probability for finding a state in cir. And that's statistical independence. The general rule is the following, that if you have statistically independent quantities, if the quantity x and the quantity y are statistically independent, then their probability distributions will factor into two independent or separate distributions, one for each of the independent quantities. So there'll be, in this case, a probability distribution for x and a separate probability distribution for y. And the overall probability distribution for both of them together is just the product of the two, and the same thing up here for the discrete case. Statistical independence is a really important property, and there's lots more to say about this, but we will save that for another day as they come up. All right, that is the end of this section. The next thing we're going to talk about is making connections between the Boltzmann distribution and thermodynamic quantities. We've made a little bit of connection so far, but not in any practical way. We've got to find a more practical and useful way to make those connections, and that's what we're going to do next, using some of the stuff that we just discussed up here in general probability.